In this paper, we present Heterogeneous Pre-trained Transformers, or HPT for short, a proprioceptive-visual robot learning method that scales between heterogeneous embodiments. The robot demos we have seen so far typically work only for a specific robot performing a specific task in a controlled environment. Unlike fields such as natural language processing, where data is homogeneous and readily available at large scales, robotics faces significant challenges due to its inherent heterogeneity. Specifically, robotics deals with three distinct data domains: human data, simulation, and real robot data. When scaling up robot data, we need foundation models that can control various embodiments, addressing challenges like changing hardware configurations, which often necessitate recollecting data. The key insight of HPT is to tokenize each embodiment dataset and use specific stems to align them within the same latent space. This method contrasts with prior works like Octo, OpenVLA, and existing multimodal learning literature, which typically rely on pre-trained tokenizers and unify the training as if it were a single task within a single domain. By aligning diverse datasets in a shared latent space, we can develop more flexible and generalized robotic policies. HPT modularizes the network through a stem, trunk, and head separation, where specific parts handle individual embodiments, while the trunk is shared across all embodiments. The core motivation behind HPT is that the shared portion of the network can be transferred to downstream tasks involving new embodiments, promoting greater flexibility and generalization. During transfer to a new embodiment, the trunk transformer can remain fixed, while only the head and stem need to be reinitialized and trained. These components typically account for just 4% of the total parameters, significantly reducing the training complexity and data requirements. To train this network, we assembled a very heterogeneous policy learning dataset with 52 individual embodiments, including real-world robot teleoperation, simulation, in-the-wild driving, and human videos. This data mixture contains 300K trajectories, and we train HPT up to 1 billion parameters. In pre-training, we observed that HPT's performance improves with either an increase in data quantity or data diversity. This means HPT can be improved when more robotic data becomes available, and that the shared trunk in HPT is capable of learning a latent embedding that is effectively shared across all embodiments, improving the model's ability to generalize and perform efficiently during inference. In the transfer learning stage, we demonstrate that HPT successfully transfers to unseen embodiments with high success rates. We show improvements in transfer learning losses when using HPT trunks compared to models that do not utilize HPT trunks. In the figure, the HPT models shown in red outperform both the no pre-trained version and the no trunk version. Additionally, the larger HPT model achieves even better performance, highlighting the benefits of scaling the model in transfer learning scenarios. The HPT architecture is compatible with various types of action prediction heads, allowing it to be adapted to state-of-the-art single-task policy methods, such as diffusion models and ACT. Our results demonstrate that the learned representations from HPT can enhance their performance and improve sample efficiency. We also demonstrated that pre-trained HPTs can be successfully transferred to two different real-world embodiment setups with minimal fine-tuning. The trained policies exhibit robustness to disturbances and new environments. The pre-trained HPT models outperform those trained from scratch. Moreover, performance improves with model scale. The larger and more thoroughly trained HPT-XL model consistently achieves better results. In the end, we demonstrate HPT's real-world performance through a few pet care skills. HPT can be fine-tuned to a water pouring task, a food scooping task, and a sweeping task. Each task is fine-tuned with 50 to 100 real-world teleoperation demos. For more information about HPT, please check out our paper or project website.